Hey everyone, welcome back to AI.Code.Cast. We're going to do a deep dive today into a coding problem that I think a lot of our listeners might have run into.
Yeah, it's a classic. It comes up all the time in text processing, data cleaning, even some compression algorithms. It's really cool. And there's so many different ways to solve it.
So what is the problem?
Okay, so imagine you have a string like a bika, and you also have this integer k. Let's say k is 3.
Right.
Our goal is to remove any groups of k adjacent characters that are the same. So in this case, we would remove the bb and we'd be left with aka.
Okay, I think I got it. So a B gets turned into a bucka because we're removing the 3 consecutive B characters.
Exactly. And there are some constraints too.
Oh, right, like what?
The string only contains lowercase English letters, and the length of the string and the value of k are going to be within a certain range. But even with these constraints, there are still many ways to solve this.
Okay, makes sense. So where do we even begin with a problem like this?
Well, I always say, start with the brute force approach. It might not be the most efficient solution, but it helps us wrap our heads around the basic logic.
Right, that makes sense.
Yeah.
So how would we solve this problem using brute force?
So with brute force, we're essentially going step by step. We're going to scan through the string, count how many times each character repeats consecutively, and if we hit that magic number k, we just remove that entire group.
And then what? We just keep repeating that process.
Yeah, exactly. We keep doing that until there are no more groups of k consecutive identical characters left to remove.
I see. So it's like we're using a pair of scissors and just snipping away those duplicate chunks as we find them.
Exactly. I like that analogy. However,
Okay.
there's a catch. Think about what happens when you have a really, really long string. You might end up scanning it multiple times, which makes it quite slow.
Oh, right. That makes sense. I guess brute force isn't always the best option.
Yeah, it can get pretty inefficient, especially for larger strings. In
Yeah.
fact, the time complexity of this approach is O and I, where n represents the length of the string.
So as our string gets longer, the time it takes to solve this problem using brute force increases quadratically. Not ideal?
Yeah, you got it. But don't worry.
Okay.
There are more efficient ways to solve this problem.
Oh, good. So how can we improve upon this brute force method? What's the first step towards a more efficient solution? Any hints you can give our AI.Code.Cast listeners?
Well, think about what's slowing us down in the brute force approach. We keep recalculating those counts of consecutive characters over and over again. Is there any way we can avoid doing that?
Avoid redundant calculations. So like maybe store those counts somewhere so we don't have to figure them out every single time, like taking notes or something.
You're on the right track.
Okay.
What if we use an array to store those counts?
And okay, so let me see if I understand this. We would have an array where each element represents the count of identical characters up to that point in the string.
Exactly. We'll call it the counts array.
All right, I like it. So for our example, a bika with k equal to 3, our counts array would look like, hold on, let me think. 1, 1, 2, 3, 1, 2, 3.
You got it. Now, instead of recounting every time we just look up the value in our array, it's like solving a smaller problem once and then just remembering the answer.
Right. So we are only doing the calculation one time and then storing it to use again later on. I can already see how this is going to be way more efficient.
What do we call this technique again?
It's called memoization.
Memoization. I'm going to have to remember that word.
It's super useful in lots of situations. And using it here actually brings our time complexity down to OM.
Wow. ON. That's a huge improvement.
Exactly. Linear time. We're processing the string in just a single pass. Of course, there's always a trade-off.
Oh, yeah. There's no such thing as a free lunch in coding. What's the catch with memoization?
Well, we're using extra space to store that counts array, so the space complexity also becomes ON.
So we gain speed, but we use more memory. That's a fair trade-off.
Yeah.
Especially if we have enough memory to spare and we really need that speed boost. Exactly. And you know what? There are even more ways to solve this problem, some using different data structures.
Like what?
A stack.
You read my mind. We could definitely use a stack for this.
Oh, a stack. I'm not really seeing how that would work.
Well, think about it this way. A stack is like a pile of plates where you can only add or remove plates from the top.
Right.
That's called last in, first out, or LIFO. And in our problem, we are also looking for groups of k consecutive identical characters, which are the last ones added to a potential sequence.
Okay, I'm starting to see it. So we could push characters onto the stack as we scan through the string.
Yeah.
And if we find k of the same character in a row, we could just pop them all off the stack.
Exactly. It's like the stack is keeping track of our potential removals.
This is so cool. I love how different data structures can be used to solve the same problem in completely different ways.
Yeah.
So how does using a stack compare to memoization in terms of efficiency?
It's actually quite similar. The time complexity for this stack approach is also ON, that nice linear time we like. And the space complexity is at most ON, since in the worst case scenario, our stack might hold almost the entire string.
So both memoization and stacks give us a really efficient way to solve this problem. But I have a feeling you have even more tricks up your sleeve.
You know me too well. Let's stick with the stack idea for a moment.
Okay.
What if instead of modifying the original string, we use the stack to reconstruct a brand new compressed string?
Whoa. Reconstruction. So we're not deleting characters, we're actually building a new string based on what's left on the stack after we've popped off all the groups of K.
You got it.
That's a really cool way to think about it. Okay, so walk me through this. We're using the stack to keep track of the characters and their counts, but this time when we hit K consecutive characters, we just pop them off the stack without actually deleting anything from the original string.
You're getting it. It's a clever twist on the stack approach.
So how do we get our final compressed string then?
Okay, so once we've processed the entire original string, we go through our stack. And for each character count pair, we add that character to our new string as many times as its count indicates.
Ah, so the stack is basically like a set of instructions for building our new string. I like how this approach preserves the original string.
Yeah.
What about time and space complexity for this stack reconstruction method? Is it the same as the regular stack approach?
Pretty much. It's still ON for time complexity, and the space complexity is at most ON, but in practice it might be much lower. It just depends on how many distinct characters we have after dividing by K.
Okay, so stack-based reconstruction gives us efficiency, it's elegant, and it even lets us keep the original string intact. But I know there's one more approach we haven't discussed yet, right? Something about two-pointers.
You have a good memory. There's one more technique that's incredibly efficient, and it involves modifying the string in place in a really clever way.
Two-pointers. Okay, I'm intrigued. Does this involve having two pointers, like, moving through the string at the same time? Maybe one, like, races ahead and looks for those consecutive duplicates while the other one cleans up behind it.
That's a perfect way to visualize it. We have what we call a fast pointer that zips through the string, and then we have a slow pointer that actually builds our compressed string within the original string itself.
So we're not deleting characters, we're just overwriting them.
Yep, exactly.
Okay, but how do these two pointers work together?
Yeah.
And how do we keep track of those consecutive duplicates?
So the fast pointer, we can call it I'm, is in charge of reading the string, and the slow pointer, which we can call J, handles the writing. As I scans through the string, we copy the character at position I to position J, basically overwriting any characters we no longer need.
So it's like we're strategically covering up those unwanted characters.
I like that.
I'm just trying to imagine it visually in my head as we're talking.
I like it.
So how do we decide which characters to overwrite?
Well, we use a counter to keep track of how many times we've seen the same character in a row. If the current character is the same as the one before it, we increment the counter. If it's different, we reset the counter back to 1.
Okay, I got it. So when that counter hits K, we know we found a group of characters to get rid of, but instead of deleting them, we just move our slow pointer J back K positions to skip over those duplicates.
You're picturing it perfectly.
Awesome. Okay, this two-pointer method sounds incredibly efficient. What's a time and space complexity for this one?
This is where the two-pointer method really shines. The time complexity is ON, just like the other efficient methods, and the space complexity is only O1.
O1. But that means we're not using any extra space at all.
Exactly. We're modifying the string directly in place.
This is incredible. So the two-pointer method is like super fast and super space efficient.
It is, but there's always a trade-off.
Oh, right, of course.
Yeah.
What's the downside?
Well, this two-pointer approach is amazing for this specific problem, but it might be harder to adapt to other string manipulation tasks.
So it's kind of like a specialist then.
Yeah, I could say that.
Okay, I'm loving this. We've covered so much ground already. We talked about brute force, memorization, two different approaches using stacks, and now this super efficient two-pointer method. It's amazing to see all these different ways to solve the same problem. So how do we decide which approach is best for a particular situation?
That's the big question, right? And the answer really depends on what you need to accomplish. Let's break down the pros and cons of each approach so our listeners can pick the right tool for the job.
Great idea. Let's do it. All right, so let's start with brute force. I mean, it's easy to understand, but that O and K time complexity makes it clear that it's best for like smaller strings or when you really need that simplicity.
Yeah, for sure. It's like your trusty old hammer. Gets the job done, but it's not the most elegant tool.
I like that. Okay, what about memorization?
Well, memorization really speeds things up. We're talking O&K time complexity. The only thing is we do use more memory with that counts array.
Right, that O in space complexity.
Mm.
But it seems like a worthwhile trade-off if you have the memory available and need that speed boost.
Totally. And then we have our stack-based approaches, both the regular one and that cool reconstruction technique.
Right. Both of those had that nice ON time complexity too.
Exactly. With the regular stack approach, you can really visualize those removals happening. And then with reconstruction, you get to keep the original string, which is pretty handy.
And even though their worst case space complexity is ON, it's often much lower depending on the actual string we're working with.
Right. You got it.
Okay, last but not least, we have the two-pointer method, our speed demon.
Gotta love that ON time complexity and that amazing O1 space complexity. You really can't beat that for efficiency.
It's perfect for those massive data sets where performance is key.
Yeah.
But I guess the downside is that it might not be as flexible for other string problems.
Yeah, that's the trade-off.
Wow. We have so many options to choose from.
It's like having a whole toolkit.
So how do we pick the best tool for the job?
Well, it depends on what we're trying to achieve. Sometimes you need that super fast, laser-focused tool. Other times you need something more versatile.
Right. So let's walk through some pseudocode for each of these approaches so our AI.Code.Cast listeners can get a better sense of how these algorithms actually work in practice.
Great idea. We won't get bogged down in specific syntax, but we can lay out the basic steps. Think of it like a blueprint.
Awesome. Let's start with brute force.
Okay, so with brute force, we'd have a loop that goes through the string character by character. Inside the loop, we'd count how many times each character repeats. And if we hit that K value, we remove those characters and update our position in the string.
Makes sense. What about memoization?
For memoization, we'd first create that counts array we talked about. Then, as we go through the string, we check if the current character is the same as the previous one. If it is, we increase the corresponding count in our array. Otherwise, we reset the count to 1. And of course, if any count reaches K, we remove those characters from a string.
I'm following along. Okay, so for the stack approaches, we start by creating an empty stack.
Exactly. And as we go through the string, we push each character and its count onto the stack. If a count hits K, we just pop those elements off the stack. And for the reconstruction method, we build a new string at the end by going through the stack and adding each character the number of times indicated by its count.
So the stack is like our little helper, keeping track of everything for us. All right, finally, let's talk about the two-pointer method. How would we approach the pseudocode for that?
Okay, so for the two-pointer method, we'd have our two pointers, I and j, representing the fast and slow pointers respectively. We also need a counter to keep track of duplicate characters. As the fast pointer moves through the string, we copy characters from its position to the slow pointer's position. We adjust our counter and move the slow pointer back by k whenever we find a group of k consecutive characters.
It's amazing how we can achieve the same result using so many different techniques.
It is, and the best part is that understanding these fundamental approaches allows you to adapt and apply them in various programming languages and scenarios.
That's so true. It's all about understanding the logic and then finding the best way to implement it based on the specific needs of your project.
Exactly. Now, one last thing to keep in mind is that the pseudocode is just a high-level overview. The actual code implementation can change depending on the programming language you're using.
Right. But the key takeaways here are the underlying concepts and the problem-solving strategies.
Absolutely.
Okay, so let's recap these different approaches and help our AI.Code.Cast listeners decide when to use which one.
Sounds good to me.
So starting with brute force again. It's easy to understand. But that ONK kind complexity means it's really only a good option for those smaller strings or when simplicity is more important than speed.
Yeah, brute force is like using a bicycle. It'll get you there eventually, but it might take a while.
I like that. So when would we want to use memoization?
Memoization is great when you need to boost performance and you have some extra memory to work with. We're talking about that ON time complexity. But we don't have to keep in mind that ON space complexity because of that counts array.
Right. So if memory isn't a concern and speed is a priority, memoization is a solid choice.
Exactly. What about the stack-based approaches? Those are pretty cool too.
Yeah, I really like those. Both the regular stack approach and the reconstruction method had that ON time complexity, which is really efficient. And I liked how the regular stack approach gave us a visual way to think about removing those duplicate characters.
Yeah, and with reconstruction, you get the added bonus of preserving the original string.
And they both have a worst-case space complexity of ON, but it's often much lower depending on the string and the value of K.
Yeah.
And then we have our superstar, the two-pointer method, ON time complexity, and O1 space complexity. It's a real winner when it comes to efficiency.
It is. But it's important to remember that it might not be as versatile as some of the other approaches. It's a bit more specialized.
So like a high-powered drill, perfect for a specific task, but not as adaptable as a multi-tool.
That's a great analogy. So yeah, it really comes down to what you're trying to accomplish.
Right. If you need raw speed and memory efficiency, the two-pointer method is your best bet. But if you need something more flexible, maybe memoization or one of the stack approaches would be a better fit.
I think that sums it up pretty well.
Awesome. So AI.Code.Cast listeners, we've explored this string manipulation problem in depth. We've seen all the different ways you can solve it, and we've even talked about the pros and cons of each approach. I hope this deep dive has been helpful.
Me too. And remember, the best way to really learn these concepts is to try them out for yourself. Experiment with different approaches. See what works best for you.
Yeah, coding is all about practice and experimentation. So thanks for joining us on this special AI.Code.Cast episode of The Deep Dive. We'll catch you next time.
Happy coding, everyone!